So here we're asked if it was possible, how long would a person need to plug into an iPhone USB wall charger in order to gain the same amount of daily energy needed by a moderately active 19 to 20-year-old man or woman? So you can imagine a scenario like what we have pictured here. So somebody's plugged into a USB port that's plugged into a wall and trying to charge themselves up for the day. So in order to figure this out, one of the first things we need to do is just figure out what's the daily energy needed by a moderately active 19 to 20-year-old man or woman. So this kind of information can be found online. If you do a Google search, you can find it. I found a site from the USDA, and it gives the calorie requirements for active men and women by age. And so for a moderately active man in the range of 19 to 20 years old, it needs 2,800 kilocalories per day. So that's for a man. And for a woman, the number of calories is 2,200 kilocalories per day. Now you're probably unfamiliar if you're from the US with the quantity kilocalorie. Normally you think about calories. When we say calories in the United States, it's actually kilocalories that we are talking about. I know it's confusing, but that's just the way we talk about it. But I'm going to be a little more precise here and just use the quantity kilocalorie. So we need about 2,800 kilocalories per day for a man, 2,200 kilocalories per day for a woman. Now, so that's what we need. Now the next question is, how much energy or how much power do we get from a USB wall charger? Okay, so again, this is information you can look up. If you do look that up, what you'll find is for a USB connection, it's the voltage is 5 volts, so it supplies 5 volts. And a typical charger operates at something like 1,000 milliamps, so 1 amp. Okay, so 1 amp of current at 5 volts is what a typical USB charger will supply. Some USB chargers will have a different amount of current, but 5 volts is pretty standard. So to find the amount of, so that's, if you want to find the power provided by a USB charger, then what you do is you multiply the voltage times the current. So it would be 5 volts times 5 volts times 1 amp. That would give you 5 watts of power. And to find the amount of energy, what you need to do is multiply the power times the time. Now, most generally what you'd do is you'd integrate. You'd take the power and integrate it over the time, from some initial time to some final time, in case the power varies with time. So if the power varies with time, you have to do the integral. In this case, we'll assume that the power is just constant at 5 watts. So this will just end up being power times the time, delta T. Okay. Now, as far as getting the amount of time that we would need to plug in, so we know how much power we have. That's the 5 watts. The energy that we need is given right over here. Now, there's a unit conversion that we'll have to make to do that. In fact, if we do that unit conversion, I'm not going to go through the details here, but you could use Google, for example, to figure out what the appropriate unit conversion is. But in terms of joules, so we're getting it in SI units. Let me erase this so we have some space. 2,800 kilocalories per day comes out to 1.17 times 10 to the 7th joules per day. And the 2,200 comes out to be 9.20 times 10 to the 6th joules per day. So we now know how much energy we need per day. Okay, so I'm going to do this on a per day basis. Okay, so that is our E here. Is 1.17 times 10 to the 7th joules and 9.2 times 10 to the 6th joules. Okay, so let's see how much time we need to get to that. Okay, so let me just rewrite that. In 1 day, we need E to be 1.17 times 10 to the 7th joules, or 9.20 times 10 to the 6th joules. All right, so then we can go ahead and solve for delta T. Right, so delta T would be that energy divided by the power. That's just coming from over here. And so, for example, we could plug in 1.17 times 10 to the 7th joules divided by our 5 watts. And this will end up giving us the amount of seconds, the number of seconds. So for that particular case, that comes out to be 2.34 times 10 to the 6th seconds, which turns out to be 651 hours. And then if we do it for the case for the woman, so that's 9.2 times 10 to the 6 joules divided by 5 watts. That would come out to be 1.84 times 10 to the 6 seconds, which is 511 hours. So clearly, this is not going to work for us. We need this many joules of energy per day, right? So this is per day, and we're showing that if we use a 5-watt power supply to get the right amount of joules we would need in one day, we'd have to have 651 hours. So clearly that's far more than one day. So in a given day, you're not going to get anywhere near enough power to keep you sustained. So you'd quickly lose energy, and that wouldn't go well for you in the long term. So plugging ourselves in, kind of like shown in the picture here, isn't really going to work for us unless we have more power being supplied to us. Okay, so we'll have to wait for that in the future. We're not going to get it with a USB port. All right, so this was just a simple example of just showing how you can calculate energy given a voltage and an amperage here. So we calculate a power here, and then how to go from power to energy. And it was just couched in terms of this kind of interesting example. Okay, we'll end it there.